Okay, this is the last talk, everybody. Congratulations on making it to the last lecture of the workshop. It's going to be about adding new models of synaptic plasticity on SpiNNaker. That's probably a bit of a general title, and it we're only going to look at STDP models, so spike timing dependent plasticity. But we'll discuss the entire framework that we've got for handling plasticity. So if you've got some other type of plastic update you'd like to apply, we can maybe talk about that afterwards. Is there anyone here that's come specifically to look at plasticity on SpiNNaker? Okay, maybe. So, but I'll try and keep this at a fairly high level then, so you get a feel for how we implement things, and if you come back to this in the future, then you know what's here. Okay. The structure of this talk, I'm going to recover first I'll start with a very brief introduction to STDP. I'm by no means an expert here. We're really here to describe how to implement this on SpiNNaker. Before we look at that in detail, in the middle there, we'll look at how we call the STDP functionality from within Pine. And then finally, I'll talk you through how we've implemented some of the typical models from the literature and how you can customize the framework we've got to implement your own learning models. So what is STDP? This is the classical quote, cells that fire together, wire together. Basically, we look for patterns of spikes from neurons connected to synapses. And if we see repeated patterns, then we try and look for some causal or anti-causal relationship. And we use that to update the weight of the synapse. So we can train the synapse to perform some specific behavior if we get some particular spiking patterns. To see what that looks like in practice, if we imagine a really simple model where we've got a presynaptic neuron here shown in red and a postsynaptic neuron shown in blue, if we get this pattern where the red neuron spikes first and then shortly afterwards this blue neuron spikes, then we say there's a causal relationship between those two events, and that will trigger some update in the weight of that synapse. The way we update that synapse is the subject of many different rules from the literature. The one I'm going to talk about mostly in this talk is an exponential relationship between the relative spike times and the amount we want to increase the weight. So we've got some exponential relationship there, and you can see using some delta t, so the time between the spikes, we can use that to provide some scaled weight update. And that increasing the weight is referred to as potentiation. Likewise, if we see that this blue neuron spikes shortly before this red neuron, then we've got this postsynaptic event before this presynaptic event, and we say there's this anti-causal relationship that this blue neuron can't have caused the red one to fire. And so we reduce the weight of that synapse. And again, we can have some rule for performing that weight change. And again, here I'm going to talk about this exponential rule where we use this change in time to predict this change in weight, and then we can apply that to our synapse. That's a very simple case, and the framework that we have to implement obviously has to cater for slightly more complex events. So perhaps where we have multiple presynaptic events before a post event. So here we've got three pre-spikes before a post spike. We have this update rule, and we can use that to calculate the contributions to potentiation from each of those pairs. So we have this first pair, well, the very first spike maybe was outside of this potentiation window, then the middle spike as it contributes this to the weight. So we increase the weight, and then we have this last pair which causes another increase in weight as well. Likewise, we can have some multiple presynaptic events after a postsynaptic event, and these will also have individual contributions which will lead to the overall weight change from those spike pairs. So the way we cater for this on SpiNNaker is we use this concept of maintaining a spike trace, and we do this for both the pre and the postsynaptic neurons. So here we've got a very simple model again. We've got neuron J and neuron I, which are the red and blue neurons respectively. And in the center of this figure, you can see the respective spike trains. And then at the top and at the bottom, this X of t and Y of t, these are the traces that we maintain, which allow us to compound multiple pre- or post-synaptic events through time. So we can have multiple presynaptic spikes, and we keep adding to this trace, so that then when we get a postsynaptic spike, we have the value of that trace, and we use that to increase our weight. And likewise, we have this postsynaptic trace, and then when we get a presynaptic spike, we can use that combination to depress this weight. So you can see for those traces and those spike times that we've got here, we see the weight change from STDP, well, varying through time from all of those different events. And you can see at the top there we've got some formulas, but what these are basically saying is the change in weight is a function of these traces, so the pre or the postsynaptic trace, depending on whether you're doing depression or potentiation, and it's also a function of the weight itself. So there are different ways, once you've got this trace, to interpret that value and turn it into a weight change. So looking now about how we implement this in Pine, I'm going to revisit the example that Christian showed in the intro lab on Tuesday. It's quite a nice way to see STDP in action. It's a very simple network. We've got a presynaptic population in red, a postsynaptic population in blue, and both of these are being fed by their own individual noise sources, so they are both receiving spikes. We then create a plastic synapse between those two populations, and we set the weight of this initially to be 0. And we also define that it's going to it can take a maximum weight of 5. And then we apply this training noise source, this one in the middle, and we fire spikes into both populations, but we have a different delay to the pre and the post population, so that we always get spikes in the pre population 4 time steps before the post population. So this means that central synapse between the two populations is going to should see a lot of potentiation events, and we should see that the synapse weights change from 0 to somewhere near that maximum. I won't go into too much detail here. By now you should know how to build this kind of model with Pine. We have to lay down some populations, define some spike rates. We can then define the noise sources and the projections, the static projections. So these ones that we join the noise sources to those populations with, they're not plastic, they have fixed weight synapses. But then we define this plasticity rule using these commands here. So in Pine, we split this plasticity rule into a timing rule and a weight rule. And this allows us to split the logic for how we compare the relative spike times and then how we convert that into a weight update. So you can see some arguments here. These relate to the relationship that I showed at the beginning. So we've got this exponential relationship between relative spike time and the contribution we want to make to the trace. And that's why we've got some time constants, and then we have a maximum value that we're going to add to that trace, and that's what these A's add. For the weight there, you can see that we have a maximum and a minimum weight that we want that synapse to be able to vary between. And later on I'll show you how those values are passed down to the code that runs on SpiNNaker. We then combine them into an STDP mechanism. Again, this is Pine functionality. So this STDP mechanism takes a timing rule and a weight rule as argument. And you can see as well here, this is where we specify the delay and the initial weight of the synapse. And then finally, we can create this plastic projection. We define the connector, similar to all of the other ways we do this, but now we have this synapse type, which is our STDP model, and it's not static. So if we run this network now, so one thing to note here, I think my colleagues have already mentioned this. STDP is where it's a significant change between 0.7 and 0.8 Pine versions. So if you've got some scripts where you've run plasticity in the past, you may find that they error out now because you've got your variables in wrong places. So if you want to convert these, you need to rearrange some of these variables. A notable change is that we add now these A values, we take them from the weight rule and we add them to the timing rule. And you can see some of the, later on in the workshops, some of the hassle that we've had making sure that we can support both of these versions with our core toolchain. But going back to the example model I showed, we can run this using these commands that you've seen before, and then if at the end we call this get weights, we should see that the array of weights there, you can see they've all increased from 0, and most of them have increased to this maximum value. And if we look at the spikes from this network, well, maybe some of these won't have increased to the maximum value because perhaps they didn't get enough training events, or perhaps there was enough noise between the pre and post populations to train them in the wrong direction. But most of these have behaved well, and if we look at the spike traces from this, you can see we now have some pretty well trained synapses. So on the left, this is pre-training. You can see we've got noise in the red pre-population and in the blue post-population. We've then got this intense training phase in the center where we've got lots of pairs of spikes. And then in this post-training phase on the right, you can see we've got noise in the blue population, so this post-synaptic population is still receiving noise, which is causing it to fire. But every time there's a spike in the pre-synaptic population, we get a corresponding spike in the post-synaptic population. So we've trained those synapses to cause those firing events. And this, I think, is one of the examples that you've already got access to, certainly in the GitHub code. So it's if you define some new training rule, then maybe it's a good example to practice with to make sure your rule is doing what you think. So this is STDP calling it from Pine. I'll now talk about how we can interface with this through the SpiNNaker toolchain. I bring this slide up. Andrew this morning talking about new neuron models. He was frequently referring to the fact you have to write Python code and C code to make this work successfully. It's the same with STDP. So there's Python code which lives on the left-hand side. This provides the interface to Pine, and then there's C code on the right-hand side, and this is what allows you to code the logic for your update rule and run it on SpiNNaker. So to develop a new STDP rule, you need to think about both things in tandem because there's a very tight coupling between both sides. To show you where the STDP code lives, okay, sorry, one other thing to mention, because it can get a bit confusing, this match between the Python and the C code, I've tried to keep this format now of having Python code with a pink background and C code with a green background, just so you know when I'm switching between the two. To show the location of the code, I appreciate this is maybe a bit hard to read, but you should have access to these slides. So you'll be able to see where in the SpiNNaker structure the STDP rules live. Those of you with good eyesight, you'll see that this is underneath STDP, and both sides you have access to the timing rules and the weight rules. So there's a good correspondence between both code stores. When we want to develop a new STDP rule on SpiNNaker, we basically have to provide 4 things. In this talk, I'm going to focus mainly on the first 2, which is the timing and the weight rule, and this allows you to define those things that we just saw being called from Pine. If you need to do more exotic things with the background framework, with how the STDP is implemented, then it may be useful to look at Synapse Dynamics and the Synapse Structure as well, and I'll talk about them a little bit at the end of the presentation. So to start with, if we want to define a new timing dependence rule, we basically have to write 2 sets of code. We have to provide some Python to allow us to interface via Pine with our rule, and this will initialize our parameters and allow us to write the data structures to be loaded onto SpiNNaker. And we've got an abstract class that you can extend to make this easy. And then on the C side, we have to compile our logic into the actual application binary, and we do this by following on by some of these templates, and we've got some good clear hooks in these which tell you where you need to implement these rules. just to give you an example, I'm going to look through the code for the spike pair rule that I showed at the beginning. So this exponential relationship between spike time and the contribution we want to make to the weight. And here I'm going to talk you through the class, first the Python code and then the C code for how we implement this. You can see here we've got timing dependent spike pair, and we extend that abstract class. And then in the initialization function, we pass this the parameters that we want to be able to use in our rule. So this is the actual thing that we're going to call through the Pine code. And so if you need to pass some variables from your Pine script down into your plasticity rule, this is where you send them in if they relate to timing. Also in this init function, we define the Synapse structure. For most cases, this weight-only function object is probably enough. But like I said, I will talk a bit more about the Synapse structure at the end of the talk. Next thing you need to do is to define some properties so you can access these variables. And then also, quite importantly, you need to define this vertex executable suffix. So this enables us to instruct a toolchain which binary to load at runtime. So we add this suffix on to the path of the binary when we're looking for an APLX to load to SpiNNaker. So if we want to load one which has got this timing rule inside, then we have to make sure we look for the one with this suffix on the end. And I'll talk a bit more about building these later on. But this pair here refers to this rule. And also in this Python class, this is where we need to manage the memory of the parameters that we want to pass in. So we need to be really careful estimating the size of these parameters. So we have to specify how many bytes of memory we're going to use. You can see here we're going to write some lookup tables for the exponential functions. So we have to estimate how much size we'll need for these. And then once we've defined this, we also have to specify how to write these parameters. And we write these data structures on the Python side, copy them to SpiNNaker, and then we'll read them from there. So it's really important that you get these things aligned, because that means we actually get what we expected when we come to read it on the C side. There's a couple of useful things in this function for good practice for SpiNNaker. I've talked here about how we're implementing this exponential relationship between the time step, the relative spike time and the contribution to the weight. As Michael mentioned this morning, calculating an exponential is quite time consuming on SpiNNaker, and so if we can avoid that, we really want to, especially within this plasticity update loop, because this will really take time out of our simulation. So where we can, we use a lookup table for this, because then it's much quicker than actually evaluating that exponential function. So you can see here there's a helper function to enable us to do this, and it takes as argument the time constants and the range over which we want to be able to write that lookup table. And it's quite a clean way of doing it, because we already know the time step resolution that we're going to solve it. But that's just general good practice. If you've got one of these complex functions that you need to use in your timing or weight rule, it's good to use a lookup table like this. I think that's an example from the Python side of what you need to do. Essentially, the difficult bits are estimating how much memory you're going to need and then writing the parameters correctly to that memory. On the C side, we then have a code file relating to our timing rule, which is going to read that data structure which we've just written. So you can see kind of the reverse here, where we're taking those lookup tables and copying them into local memory. So these data structures will first get written into SDRAM, and then we need to copy them locally so that they can be used in our rules. It's very good practice to do some checks here to make sure you've got the data structures that you expected. So to do some checks on the numbers, check that you've got the right precision and that you've used the right data types. And this is a good place to put some logs, because this only gets executed during an initialization phase at the beginning of a run. We then have a header file where we keep the functions for implementing the timing rule. And this is where we end up digging into these are essentially the hooks that connect to the rest of the STDP framework. And there's basically 4 functions in this file, and this is where the real core of your timing rule is implemented, or the whole plasticity rule is implemented. The first one of these functions is called timing add pre-spike, and if we go back to this very simple 2-neuron model, and we imagine we've got a neuron which can fire, it's this function which creates the trace that we see at the top there. So for this simple exponential relationship, here we add some contribution, and this is where, if we get multiple pre-spikes, we can combine them so we maintain this trace. Okay? Hope that makes sense to everyone. So this is basically taking that trace forward, and needs to be able to be updatable in this way that you can have a new event at any time, and this trace will be able to be maintained. So I mentioned there's 4 functions. As you might imagine, there is a corresponding function for adding a post spike, so we can maintain this post spike trace, and again there's this way to compound the trace so that we can then use it later on. So that's 2 of the functions. The third and fourth are how we then use that trace to instigate the update. And so if we've had a couple of post-synaptic events like this, and we've got this post trace, and then we receive a pre-synaptic spike, this function is basically what tells us how to use that post trace, the relatives, and use that relative timing to evaluate the trace value, which can then be passed to our potentiation or depression rule. So the code here, you can see it takes quite a lot of arguments, and so it's quite a general STDP framework. And this example here, we don't necessarily need to use all of those items that have been passed in. They're there because they give us the flexibility to do whatever any kind of rule might need. So we've got things like the current time, the time of the last pre-spike, the time of the last post-spike, and we've also got the value of both traces and the previous update states as well. So with all these things, you can do any kind of logic that you might need to be able to update the neuron weight. And the last thing we do is we actually use a function from this weight rule, and because of this pairing, the ordering of this pairing, this will actually apply depression. So you can see in the blue box there, we call this function from the weight rule, which I will talk about a bit more later, but we pass the value of this trace at the time of this presynaptic spike, and then that will be what actually does the depression of the synapse. Okay, and you can see now the synapse has changed size. Correspondingly, the fourth function that we define here is how we do the reverse. So for potentiation, so if we've got some presynaptic trace and then we get a postsynaptic spike, it's this function which enables us to calculate the value of that trace at the time of this spike, and it's then that trace that we use in this weight function to apply the potentiation. I hope that's clear. If anyone's got any specific questions about this, maybe we can take it offline afterwards. And this obviously will cause the weight of that synapse to be increased. So this is the framework. Obviously the sister part to this is defining how we execute the weight update. It follows a very similar path to doing the timing rule. And again, we have to write some Python code and some C code. The Python code is what allows us to interface to Pine, and then the C code is what gets executed on SpiNNaker. And again, we have an abstract class to extend, and this is the thing that we call within our Pine script. So if you've got some values that you want to pass to your weight rule, you pass them through this through this class. And there are some similar methods here. An important one being, again, how we define this vertex executable suffix. So the whole concept of Pine is to use this modular approach, so we can have a separate timing and weight rule, so we can have different mix and match between these two things. So it's really important to get this right, so that when we build our binary, we get the right pairing, and we actually find the APLX to load to SpiNNaker. Again, we have to specify our memory requirements. Here, this is perhaps a more clear example. We've got 4 32-bit parameters, so we end up needing 16 bytes per synapse type. And we obviously have to specify how to write these as well. And you can see here how we write these as, I think they're all 32-bit integers. At the bottom, again, is another good bit of practice for SpiNNaker. We've written these the minimum and maximum weights, and these are scaled by W here, which is a SpiNNaker thing we need to do to make good use of the fixed point range. But at the bottom, we also pre-calculate some multiplications that we know we're going to have to do at runtime. So rather than leaving them to be done on SpiNNaker, we do them on the host beforehand. And this saves those operations having to be done at runtime and slowing things down. So we've got 4 values that we've written there. This, I think, is the end of the Python code, yes. And so we write a corresponding code file on the C side, and this is what reads those values, much in the same way as I described earlier. Here at the bottom, you can see we've written some log statements to enable us to check that we've defined the correct parameters there. On the weight rule, there are a few different functions. One is this get initial weight, and this enables us to create a state that we can edit rather than operating directly on the value from the synaptic row. We then have these 2 functions, and these are what you saw being called from the timing rule. So we have a way to depress and potentiate the synapse. Again, here we've got this additive rule, so you can see it's very simple. We just add on a contribution or take away. Well, they're both additive. You'll see we have a difference. We use a negative when we collect them at the end. And then there's this calculate final weight, where we evaluate all contributions to that synaptic update, and we can then commit them back to the synapse, and we return this new weight at the end. That's then given back to the framework, which is then written back to the synaptic row, so that's the new weight that will be used for that synapse. Okay. The build is very similar to you've seen when you're defining a new neuron model. So we take a build directory within the SpiNNaker framework. We prefix this with the name of the neuron model that we want to use, and then if we want to include plasticity, we add STDP mad on the end. We then add an underscore, and then this is where those vertex executable suffixes come in, and so we then add on the name of the timing rule and the name of the weight rule, and that's how we build up the string that we use to find the binary that we want to load to SpiNNaker at runtime. So when you're building your new neuron model, including this plasticity, it's really important that you get the name of the build directory right. Inside the build directory, you then have a makefile, exactly the same as you saw this morning. The first part of that, again, is exactly the same, and you've got these variables pointing to the neuron model and the input type and threshold and synapse types. But then at the bottom here, you have the variables defining where the plasticity code is going to come from. I'd recommend sticking to this standard Synapse Dynamics for when you start developing any new STDP rules. But you can define your own timing and weight rules here like this. And if you want to make the toolchain build this along with all of the other code, you can add it to the parent makefile as well. There are already quite a few different rules implemented on SpiNNaker. So if you're looking to develop something new, this is quite a good place to start. There's a good chance someone may have already done something that you're interested in. And now you can start to see the usefulness of having this modular approach. So you can use one timing rule with multiple different weight rules and vice versa. So providing the underlying data handling is going to be consistent, then it's quite easy to change between them. And you can easily add them to do different neuron models as well. So the Synapse Dynamics, this it basically defines the background framework which will call the code that I've just described. But there's some useful things to consider here from a SpiNNaker specific point of view. And if I come back to my really simple model, which has got two neurons in separate populations and they're connected by this plastic synapse, they will be, by default, they will be running on separate cores on SpiNNaker, and so they won't have any shared communication, but being able to send spikes. And this has some effects on when we can do certain things with the plastic update. So if we imagine the red neuron fires and sends a spike to this blue neuron, and then it causes this blue neuron to fire itself, excuse me, then we know that this should perhaps cause some potentiation effect. And likewise, if this red neuron fires again, this will cause depression. I think I've got that, yeah. But you need to understand a bit now about where we can actually perform the update to the synapse value, weight value. And because of the way SpiNNaker is structured, we actually only do this when we get a presynaptic spike. So we make use of the fact that when this red neuron has fired and sent a spike to the blue neuron has had to go into the SDRAM and retrieve the value of the weight associated with that synapse. And this means that because we've already retrieved that value, it's quite a convenient time to do the plastic update. And so we constrain the system to only change the weight when we receive a spike at the blue neuron here. So we're constrained, we call it a pre-sensitive system. So we only do this update at this time, but we store the both of these events in history so that we can, when that spike arrives, we can do the potentiation and the depression at that point in time. But it's quite useful to keep that in mind if you are trying to debug an STDP mechanism, because you may find the updates don't happen exactly the times you're expecting. And so to continue this on, perhaps now if we got multiple postsynaptic events, we know that that will cause potentiation, but until we receive another presynaptic spike, we won't actually commit those potentiations to the new weight. So we'll just keep them in memory and wait, and then when we receive this presynaptic spike again, that's when we can come back, apply these potentiations. Maybe this depression is outside of a window, and then we've performed our weight update. And maybe now, because we've got such a big weight on that synapse, we end up with another postsynaptic spike. But the take home here is that it's a pre-event sensitive system, and we only perform potentiation and depression on the postsynaptic core. You could configure this differently. We've done it this way as it's the most efficient way to use the hardware, but if there was some specific rule that you wanted to do things differently, then it's possible to change the underlying framework and call things in a different order. So the last thing to talk about is the synapse structure. This essentially is the data structure that we've got in the synaptic row relating to a particular connection between two neurons. So in most cases, like I said, you only need a weight value there. So we just have a single data structure in here. And we have some Python code and some C code to define this. And you can see for the majority of cases here, we just write a 16-bit weight term. And if we want to read this back at the end of the simulation, you need to define this bottom function. And this will be designed to replicate that data type. And so we'll return this 16-bit weight as well. But if your STDP rule needs to maintain a per synapse value other than the weight, maybe you need to look at some other count of events or something, then it's possible to extend this data type here and add extra objects into this synapse structure. But obviously that means you need to define the extra structures in this get synaptic data function, and also if you want to read them back at the end of your simulation, you need to update this read synaptic data as well. And as with all of these things, there is the corresponding code on the C side, which interprets that data structure Here we've got a very simple one because we just only have this single plastic weight. But if you wanted to add new things in here, then this is where you would take the data structures you've written with the Python code and initialize them ready for runtime. Again, I wouldn't start there if you want to implement a new STDP rule. It's better to start with the weight and timing updates and then get a feel for how these things work, and then look at changing them. So the overall framework, I've talked about quite a few different files and frameworks there. We basically have 4 things you need to define, and they each have a C and a Python component. We've got our timing and our weight dependence rules, and these are classes that we call via Pine, and this is where we pass things into the STDP rule from a Pine script. We've got the Synapse Dynamics framework. This is called by the SpiNNaker toolchain, and by default we use this STDP MAD framework. The Synapse Structure is defined via the timing dependence, so there's no separate way of calling that. You do that in the initialization of your timing rule. On the C side, again, the Synapse Structure is included through the timing rule, and then we specify the timing rule, the weight rule, and the Synapse Dynamics all in the make file. And the workshop now, if you are interested in this, will take you through the steps of how you can create your own set of these files and then compile them and then call them from Pine. So you'll get a feel for how to pass variables around and the overall structure of all of this. So to summarize, we've got SpiNNaker, this API which sits on top of SpiNNaker for doing the Pine neural network modeling. It's got a flexible STDP framework which enables us to specify these modular timing and weight rules. They've all got this split Python and C implementation, so you have to write code to run on the host and on SpiNNaker, but they have a very tight coupling, both in terms of the data and the rule they implement. Can't recommend enough looking at the existing implementations if you want to get some tips about how to do something new. There's good examples of how to write particular data types, how to do lookup tables, all this kind of thing, and it's quite easy then to take some of that code and embed it in your custom rules. And I wanted to just finish by saying a bit about what we're doing in the group at the moment. I was hoping the PhD students responsible for this were going to be here. A couple of projects we've got ongoing are looking at neuromodulation. So what I've described up to now is kind of classical Hebbian learning, but Mantas in our group, I think he was here on Tuesday, is looking at this neo-Hebbian three-factor learning, when we can have some kind of neuromodulator signal which enables us to switch on and off learning. And he's got a paper which I think should be coming out soon, and once that's published we'll look to incorporate this into our master version of the toolchain. And Peter, another PhD student, is looking at synaptic rewiring, so the actual generation of new synapses depending on the network behavior. And he would be much better at describing this video than I am. But basically he's looking at building networks which can create new connections based on local activity. Maybe he'll be around later, and he's the best person to talk to about this. And that brings me to the end of the STDP on SpiNNaker talk.